for the introduction, and also thanks for inviting me here. So I will talk about lower bounds on the running time for scheduling and packing problems. So this is joint work with Lin Chen. He was a student for 1 year from China in Kiel. Two of my other students, Felix and Kati Land, and Ko Chang, who is the advisor of Lin in China. So under the assumption that P is not NP equal to NP, you can see the picture like this. So we have the class of all polynomial time algorithms. NP and 3-sat lies somehow in the difference, and we can only claim that 3-sat is not polynomial solvable. And what nice is by this workshop or this community is to proving some better bounds. And one thing is to see this as a landscape with different running times of algorithms. So 2 to the square root of k, where k is a parameter, or 2 to O of k, also what we have seen in the first talk by Fedor. And so natural parameter, what we have also seen for 3-sat is the number of variables or the number of clauses. And what we use mainly to proving the lower bounds is using the exponential time hypothesis, so that 3-sat formulas with m clauses and n variables cannot solve in this time 2 to delta n times a polynomial and n and m. And what's also important is the specification, so that we can use instead of n here, m the number of clauses. That's important because if you want to transform or do some reductions, then it has to relate to m. And if you would use n, then you would get a worse lower bound afterwards. And so actually, at some point, I read this nice survey by Daniel Marx and some others about the ETH and consequences, and I saw there are many results, especially for graph theoretical problems, but only few for some scheduling or packing problems. There was one, for instance, for scheduling with precedence constraints. There was one for two-dimensional vector knapsack. And with Daniel Marx, I also proved some results for unary bin packing. But looking at this, I thought it's a good point to start work more on this. So with Lin Chen and Kati and Felix, we started to do this, wrote a proposal to the DFG, and the stories could start, and we got more and more results in this direction. And I will show you some of them. So we worked mainly on exact and approximation algorithms, and to see if we can get lower bounds for both. So the main goal was for me to find bounds for scheduling and packing problems, especially proving lower bounds based on the ETH, and also sometimes to find algorithms with some upper bounds, and the best case clearly to find matching lower and upper bounds. Some cases it's possible. I was surprised that in several cases really you come very close to the upper bounds, so that my feeling was that so the ETH should be very useful, and I believe in it. Otherwise I could not get such results. So I start with exact algorithms and show you one example, what most of you probably know. And I show you that subset sum partition and other problems cannot be solved in this time to do little o of n. And there are also some matching upper bounds for this, what we have seen also in one talk before in the morning. Most of the algorithms are based also for the scheduling problems on subsets of the jobs. So you enumerate the subset of the jobs at the beginning, at time t, and then you continue and always have to store by some dynamic programming subset of sets that you have executed already. And then you get algorithms with running times 2 to O of n. So how you can prove this result? And I found in a book by Ingo Wegener a very nice reduction that gives you directly the proof. And therefore, I think it's good that everybody knows about this. So we have n variables here, m clauses. And for each variable, you create two items. So a truth and a false variable, where here you count at this side the variable with the index I. And then you look at all positions in the clauses where the variable is inside and mark this here at the corresponding higher positions. And here you do the same for the negated variables. And in addition, you have two dummy items for each clause. So what you can see, they somehow are used to match the bound 3 at the corresponding position. So let us look at an example. So here's a reduction. So we have two clauses, three variables, and you see here are the corresponding indices for the variables in both cases. And for instance, x1 is in the second clause, therefore we have a 1 here. And x1 bar, this one is in the first clause, therefore we have a 1 at this position. So it encodes directly the corresponding containment of variables in the corresponding clauses. And then you can see we have here the dummy items. And what's important for the reduction is, so there are no carryovers if you take solutions like this, because you have only here, we have only 2 ones. And here in the worst case, we have 5, because we have the 3-side formula. So that cannot happen if you select anything that you somehow get here a value larger than t and it goes over to the next position. That does not happen here. That's important. So if you look at a specific assignment, so let us choose x1 and x3 to true. We have these true positions, and here we have the false for x2. You see automatically the variable setting is already done. And then you have to choose here two dummy items that it fits directly together. And so you see this is the corresponding subset sum solution, what you get out of this. There's a direct correspondence between both things. So what you see by the reduction, what was known as the 3-side formula is satisfiable if the constructed subset sum has a solution. But what's nice is here, the constructed instance has only 8m items. It's linear in the number of clauses. So that means it gives a strong linear reduction. Therefore, if you have an algorithm for subset sum in this running time, this gives automatically an algorithm to decide 3-side, and it would has a consequence that the ETH is false. So that shows you very easily that this works. And we use that also as a basic later to prove some other results. So what's interesting is also, you could also look at the size of the constructed instance of all the numbers. So we have 2n plus 2m plus 1 numbers here, and we have 2n n plus m positions. So it means the total size of the instance can be bounded by the m square. That has the consequence that you can also prove you cannot solve the problem in 2 to square root of the input size. And also what's interesting, there are also some matching upper bounds where you have here a running time 2 to big O of this the size here. For subset sum and also for the knapsack problem. You can find this. So that was surprisingly for us that it also works. So for the scheduling problem, the situation is a bit more difficult. So for 2 machines, you get the same result as before. But if you have also m machines here, this is the standard notation for scheduling on identical machines while minimizing the make span. You get a lower bound like this here, so m, so almost the square root of m goes inside of the exponent here. And on the other hand, by dynamic programming, you can also find an algorithm that comes close to this, but you need here some log factor inside. It's not clear what the best result is here. So now let us switch to approximation schemes. So I worked a lot on approximation schemes for Knapsack or also scheduling problems. And I wanted to know, are there some lower bounds for this? For some problems it was easy, for others more complicated. The first thing is for the multiple knapsack problem. So you have several knapsacks, maybe of different capacities. You want to find a subset of the items that fit into the knapsacks while minimizing the overall profit. There is an algorithm, what I developed some time ago, that has a running time 2 to O of 1 over epsilon times some log factors. And you can prove on the other hand also there's a lower bound, so there's no algorithm with such a running time, where here is little O of 1 over epsilon. And that holds also for some special case, where you have only two knapsacks of the same capacity, and either one of these two cases. So very simple case, the first one, all items have the same profit, so you want only to know the number of items that you can pack. And in the other case is maximizing the overall size of the items. So what is the main idea to prove this? So what you can consider is a restricted version of the knapsack problem. So we have two knapsacks, as I've shown you, and let's choose a capacity, it's 1/2 of the total size. So I would like to pack everything inside. So I assume here that the total size is an even number, otherwise I have automatically a no instance. And then I need an upper bound, so I need a value c, so that the coding length of c is polynomial in the size of the corresponding partition problem, where I have only the sizes inside. And then the profit values should be like this. Every item has a profit at least the value c. And it's the overall profit of all items is bounded by the value c times alpha and the number of items, n. And alpha should be constant here. So let us assume that we have such a restricted version. I will show you later how to obtain these in both cases. The idea now, you take an instance of the partition problem where we know by our previous reduction that there's no good algorithm for this, and reduce it to the restricted version of the multiple knapsack problem, where the sizes remain the same. I don't change the sizes of the items. So the point is, if there's a solution for the partition problem, then automatically you see there's also packing in the two corresponding knapsacks that you can use. Now, suppose that you have an approximation scheme for the multiple knapsack problem that finds an 1 plus epsilon solution in this running time here. Next step is you set epsilon to 1 divided by alpha n. So what follows then? The claim is that the approximation scheme packs all items if the partition problem has a solution. So first of all, you use the bound here for the profit, and then you get a lower bound of the value c. And then if you know all items are packed, the algorithm, the scheme has a profit at least 1 divided by this times the optimum value. This is by the definition of the scheme. The optimum value, if all items can be packed, is the profit of all items. So, and then by some calculations you can see that this value is at least the overall profit minus the value c, using this inequality there. But on the other hand, the profit of each item is at least c. That means there cannot be any unpacked item because the profit was already larger, because you had this larger than here inside, and the claim follows then automatically. So now you have to use the running time. So we can decide whether the partition instance has a solution by running simply the 1 plus epsilon approximation algorithm. So what's important is, by these two bounds, you can prove that the input length of your restricted version here is also bounded by the input size of your partition problem to some polynomial. So you have to calculate carefully here and use these bounds here. And then if you use this corresponding epsilon value and insert this running time goes over to this running time. And this is a running time for the partition problem where we know we don't have this, only if the ETH falls. So, and this gives you automatically the result. So what remains is to construct these corresponding restricted versions. The first case is quite easy if the profit is always 1. So you take a partition instance and simply take the sizes and choose always the profit equal 1. So then we see the profit of all items is the number of items n. The profit is at least 1. So you can choose alpha 1 and c equal 1 and you are done. So the bounds for c they hold and that's fine. So that's the simplest case. The other case is a bit more complicated. You have to use an intermediate problem, a partition problem where the sizes are not too small and not too big. So you need a value c here where the sizes are between c and 3c. But you can construct this by a reduction from the partition problem also. That means you can also prove that there's no algorithm that decides the specific partition problem in this time. So this property here, these inequalities for all items, shows that the overall size of all items is bounded by 3cn. The profit is always like the size. So we get an upper bound like here and the lower bound automatically here, no? Because it's exactly the size. So that means you can choose the value alpha 3 and you choose the corresponding value c, what you get there. And you see also the value c satisfies the inequality. No? That's important here. Where was it? Yeah, you have to check that the encoding length of c is bounded by the size or a polynomial of this. It is enough. So then you have a restricted version here of the corresponding Knapsack problem, and the same thing as what I've shown you before works. Okay. We looked also at the two-dimensional vector packing problem. I've shown you there was a result by Hadas and Kulik, and could improve this further. So here was the square root of 1 over epsilon. You get this lower bound now, unless the ETH fails. In the other result, there was a weaker assumption now by Hadas. But what's nice is there is also an upper bound for this by Caprara and others that prove such a running time. So for the two-dimensional case that matches. What we don't know is what happens in the higher dimensional case. In the higher dimensional case, there is an algorithm where the dimension goes here in the exponent, but we were not able to prove a lower bound here where d goes inside. So that maybe there is a better lower bound or a better algorithm. So that's one interesting thing one can work on. So the last thing is we worked also on the scheduling problem on identical machines. In the Soda paper with Lin and Gochang, we proved the lower bound like this here. For any delta, you get that as a lower bound. That means that comes very close to little o of 1 over epsilon. And there's an upper bound, so what I proved some years ago, for identical and uniform machines, where we have is 1 over epsilon square inside. So that means you have also here something where is a little gap, but fortunately recently we were able to improve this. So you get here 1 over epsilon. So we are writing this up now, this together with another student and Josef Hershey from Santiago. So we, by some clever techniques about the configuration IRP, we could reduce the running time here. But we had also some results if you specify the number of machines. So if m is constant in this case, or as a parameter, you get a lower bound where m goes here in the exponent. So that means you can here claim that there is no specific fp-task for the problem. On the other hand, there is also an fp-task even for a more general problem with unrelated machines that is harder to solve, where you get these running times. And here you see that comes also very close to this under this specific case here. If the epsilon should be smaller than 1/m, then you get this. So this I did with a former PhD student, Monaldo Mastroielli from Lugano. Here's maybe a nice story about this. So we worked on this. It's not published, this result. So because people thought maybe it's not interesting enough, but maybe it's more interesting because we have this lower bound. So see that this is matching. Okay, as a summary, so if you are interested, you can look at the papers. One is at Watts and the other was at Soda. Open problems are, what I think is interesting, the d-dimensional vector Knapsack problem or closing the gap. The main complicated things are the log factors inside, but they are not so easy to solve. There are some underlying problems that are quite hard. For instance, if you would like to improve this here for the multiple knapsack problem, you have somehow to work on bin packing problem instances. And if you can show, for instance, that the modified roundup property holds, so that means the optimum number of bins what you need is bounded by the LP value rounded up +1, so then you can improve the running time for the multiple knapsack problem. Another thing what's inside here in the scheduling part is we use a ILP, so a result by Lenstra or an improvement by Canon, where you have a running time d to O of d, where d is the number of integral variables. So there's hope that you can improve this to 2 O of d, and that automatically would also improve this result then, no? If it holds also for the identical automatically, and for the uniform case, you would need also a result about mixed integer linear programs. So for uniform case is a bit more complicated. So that's it. Thanks.
Klaus, I have a question. There's this famous problem that's in the Gary and Jansen list in the back of the 10 open problems. And it's K processor scheduling, unit task length, precedence constrained scheduling. And I think the current state is that it's known to be polynomial for 1 and 2 machines, and there was a claim for many years that it was polynomial for 3 that nobody ever saw proof. And Hans and I, Goldmander and I had a paper a long time ago where we purported to show that it was hard for W1 by a reduction from clique, I suppose, or something like that. Or maybe it was dominating. Somebody recently wrote and said that our proof was flawed. I'm not quite sure what the current state is. But couldn't you, using ETH, conceivably show like a lower bound of no n to the k minus delta, even though you don't know that the problem is actually in XP? Because you code in something like correctly.
Maybe you can prove, but there's a recent paper by Rotfors, it was on Archive. He proved if you use the laser hierarchy, so that you get some results, but if I remember, it's not a polynomial algorithm what you get, but it's somehow pseudo-polynomial that gives something in the exponent. But it seems a promising direction using mathematical programming techniques to improve this. Or maybe that is also the border, no? And then you can prove also lower bounds, but I'm not sure, no? What can be done?
Maybe one concrete question. What are the exact figures for d equals 3 for this d-dimensional vector knapsack stuff?
The exact numbers?
Yeah, you mentioned that there is with d.
I think in the exponent, if I make no mistake, is d minus 1 goes in the exponent.
Okay, so squared basically.
Yeah, squared divided by epsilon. The epsilon remains there.
Yes. And what was the lower bound?
Lower bound is only what we have, so I don't know what happens, how the d goes inside, no?
Because I can, three dimensions, I can still imagine.
Yeah. But that's an interesting thing, no, to work on, no? There's some results for related problems by Nikhil Bansal, but maybe can be used, no? So I'm not sure. He did some work about the vector scheduling problem, if I remember correctly.